So today we're going to be talking about combining functions. So let's say that we have two functions, f of x and g of x, and they can be two different things, and we'll look at some examples later. But for right now, we can talk about what we can do with those functions and how we would write them. So let's say we're going to add two functions, f and g. Okay, so f plus g of x. If it's ever written like this, what it's really saying is, what is f of x plus g of x? Okay, we can difference, remember, means subtraction, so we can subtract these. So that would be you could see it written as this: f minus g of x, which is just f of x minus g of x. We can have a product multiplying, so that would be like f times g of x, which we would write it as f of x times g of x. Or we can also have the quotient of functions, which you could see written like this: f over g of x, which is really just saying f of x divided by g of x. Okay, so there's lots of ways that we can combine functions. And so let's look at a couple examples now. All right, so let's look at two different specific functions. We're going to look at the function, we're going to say p of x equals negative 2x. And we're going to look at r of x as the function x plus 4. Okay, and so what we're going to do is we're actually going to do all four of our functions, right? So let's look at p plus r of x. Okay, well, p plus r of x is really just saying, what is p of x plus r of x? Which is, well, p of x is negative 2x plus, and then r of x is x plus 4. And then all we're going to do is just combine when we can. So negative 2x plus x is just going to be negative x, and then the plus 4 tags along. There's our first one. Okay, let's look at p minus r of x. Okay, so that's really just p of x minus r of x. So it's negative 2x minus x plus 4. Now this one's a little tricky because you have to remember that we're subtracting the whole function. When we're adding, it doesn't really matter. But subtracting, we have to remember to distribute that negative sign. And so that's really a negative x and a negative 4. And so when we combine those, the first part you'd be okay with. Negative 2x plus x would be negative 3x. But the second part, it's plus a negative 4, so it's minus 4. And that would be an easy mistake to make, so we have to be careful with that. Let's look at the next one, which is going to be p times r of x. Okay, and so remember, p of x times r of x, that's times. And so we get negative 2x times x plus 4. So negative 2x times x is negative 2x squared, and negative 2x times 4 is minus 8x. Okay, so far so good. All we're doing is just combining all of them. And then finally, the last one is p divided by r of x. Okay, well, p of x, remember, I guess it's p of x divided by r of x. And so we would get negative 2x divided by x plus 4. Now there is one caveat we have to remember, that x cannot be negative 4. And that's because negative 4 is not in the domain of this function, because the bottom can't be 0, so we can't have negative 4. But everything else works. Okay, very good. Now we're going to talk about evaluating. Okay, now how do we evaluate these? Okay, well, the way we're going to evaluate is basically it's going to give us some value, and our job is to actually just plug those numbers in for a given value, right? So if, for example, okay, they were going to say, okay, we'll go back to our P of X being negative 2x and our R of X being X plus 4, right? Let's say that they actually tell us to evaluate P times R of negative 2. So really, what they're saying is, what is P of negative 2 times R of negative 2? So if we think about that, I'll just keep writing down. So P, remember, would be negative 2 times negative 2 times, and then we would be doing negative 2 plus 4, right? Because we're looking at the two functions separately. And so negative 2 times negative 2 would be a positive 4 times, and then negative 2 plus 4 would be 2. And so then we'd end up getting 8. Okay, so now here's the question. The question is, we did it separately, right? We put it into P and into R, multiplied it out, and got 8. But before and above hand, we found out that this was equivalent to, when we just had it of P of R of X, right? P R of X, we actually said that that was negative 2x squared minus 8x. So do you think it's the same? Do you think it's 8 if I was to put negative 4 up here? Okay, put a question mark. Okay, well, let's figure it out. So if we're going to look at that one, okay, let's put a negative 2 in for x. So we get, I'll do it in green down here. So negative 2 times negative 2 squared minus 8 times negative 2. And so when I do this, negative 2 squared is 4. So negative 2 times 4 would be negative 8. And then plus 16, because negative 8 times negative 2 is positive 16. And when I add those, I get 8. So check it out. It's the same thing. So does it matter which way you do it? It does not. Both give you the same answer. All right, so this is a new equation that you have not seen before. This is called the difference quotient. It's essentially finding, it's the beginnings of finding a slope, but of functions, right? It's just basically finding out an average rate of change between two different functions. Well, it's the same function, but two different values. It's finding that rate of change. And there's different reasons why we take rates of change for in different locations versus an overall. And so if you kind of look at this graph right here, if I was to just draw a single line the whole way, you notice sometimes it's above and sometimes it's below and sometimes it's above and sometimes it's below. So if I was going to find, how far every data point was from this center line, right? If I was going to look at that, it averages out to pretty much 0 because sometimes it's above and sometimes it's below. So what we do as mathematicians is we look at a certain value, okay, because it changes so much. Kind of like when we see the change in seasons, right? As seasons change, the amount of time of daylight you get increases and then gradually decreases. And so we like to see, this amount right here, we like to see what the data changes all the time. Okay, so we use what's called the difference quotient. Okay, it's kind of a long backstory for what we're doing here. But anyway, here is the equation right here. It's f of a plus h minus f of a all over h. So let's look at a problem here. We're going to look specifically at f of x equals negative 3x plus 8. Okay, so we're going to find the difference quotient. So remember our equation for it is f of a plus h minus f of a all over h. So what we're going to do is we're actually going to change, instead of f of x, we're actually just going to use a's and h's, right? But we're going to substitute them in because remember functions, right? When we have an a plus h, we're really substituting it in for x. So let's do that. Okay, so I'm going to rewrite my formula using this function specifically. So our function using f of a plus h is negative 3 a plus h plus 8. Okay, that whole thing, all right, minus, and I'm going to do this in full parentheses because it's a new function, negative 3a plus 8. So remember, all I did is I just put in a for x, all over h. And we're going to see what happens, okay? So we simplify it out like we would do any problem. Negative 3 times a, negative 3 times h. So it's negative 3a h plus 8, okay? And then minus a negative. Remember, we have to distribute the negative sign. So minus a negative is plus 3a. Actually, you know what? Strike that for a second. Okay, negative 3 times a is negative 3a minus negative 3 times h. So negative 3h plus 8 plus 3a, and then subtract 8, and that's all over h. And so what I end up getting is, okay, so you'll notice if I'm simplifying, because that's what we said we're doing, negative 3a plus 3a, so those cancel out. And then plus 8 minus 8, those cancel out. And so all I get is negative 3h over h, which ends up being negative 3. Okay? So if you look at it, you can notice some things that maybe look a little bit different. But this right here is something similar to this. Okay? And so the more you practice these, the more they'll make sense. And so I strongly urge you to take a look at a few more problems like that. Now, example 4 says finding average rate of change. So this, we use average rate of change a lot for, finding specifically how something changes over a period of time. So we'll look at a word problem. I'll read it to you, and then I'll write down some important information. Okay, so suppose a ball is released from the top of a hill, and the distance in feet that the ball rolls from the top of the function of the hill t seconds after it's let go is given by the function d of t is equal to 5.7 t squared. Okay, so d of t, our distance in time, is equal to 5.7 times t squared. Okay, find the ball's average speed between 7 and 12 seconds. Okay, so what we're trying to do is basically find, okay, so relating it back to the previous problem, okay, f of a plus h minus f of a all over h, right? So let's think about it in terms of time. When we're looking at time being 7 seconds and 12 seconds. Okay, so what's this really saying? What's this function saying in context of these problems? What we're going to do is we're going to look at our function, a being the original time. So that would be at time 7 seconds. So a plus some h amount. And we want h to be some number that gives us 7 to 12. So really, we're going to be looking at this. The function, or actually we're going to use our function as d, distance. Distance at time 12 minus distance at time 7 divided by, and what we're dividing by is basically what am I adding 7 to get 12? So h is that difference, which is 5, right? And so what we're going to do here is we'll find d at time 12, okay? So 5.7 times 12 squared is 820.8 minus, then we find the distance at time 7, which is 279.3, all over h, which is the change in time, which is 5 seconds. And so we'll just simplify. So we get 541.5 over 5, which is 108.3. And so then your question is, okay, well, what does that mean? What it means is remember, we're looking at distance by time, okay? And so that's our average rate, okay? Distance over time. And so that means for every second, right, because these were different seconds, this is going to be going 108.3 meters, or what does it say, in feet. So this is feet per second. Okay, 108.3 feet per second. So it might not always be moving that fast. It might be moving a lot faster, or it might be moving a lot slower, but that's the average rate of speed between our time frame of 7 and 12 seconds. All right, and so one of the last and final things we want to talk about is composition of functions. So what is composition of functions? Well, composition of functions is when we have two functions, we'll say f of x and g of x, and we can put them together, basically putting one of them into the other. And so our composition of functions is something I like to call the Fogg and Goff problems. So f of g of x, okay, looks like the word fog, but it's a little o, okay, or a little circle. F of g of x is equal to f of g of x, okay? Or we can have another way I like to call it is the Goff problems, which is equivalent to g of f of x, okay? Now, why would we want to know how to evaluate, or how would we want to know what to do with one of these? Well, sometimes when we have two defined functions, our final product is going to change based upon what something else did. So let's say we're trying to find how much ice cream you're going to make. Okay, well, first off, you got to know how much cream you're going to have, okay, which is dependent on how much milk you get. So you put the milk in, and you get cream, and then from the cream, then you can figure out ice cream. Okay, so it's all like compiling. It's like one of those Matryoshka dolls. They kind of go inside of each other. So that's kind of what composition of functions are. Okay, so we're going to look at a problem. Okay, so let's say I have two functions. Okay, I'll give you, in fact, we're going to use our p and r again. So p of x, remember, was negative 2x, and r of x was x plus 4. Okay, so we're going to look at both ways of composites. Okay, so we're going to do p of r of x, okay, which is p of r of x, which means I'm looking for p of, remember, r of x right here is x plus 4. And so p of x plus 4 would be, okay, well, that means whenever I see x right here, I'm going to put x plus 4. So that's going to be equivalent to negative 2 times x plus 4. And so negative 2 times x is negative 2x, and negative 2 times 4 is negative 8. So there is p of r of x. Okay. Now, the question is r of p of x going to be the same thing? Okay. So let's figure out what that is. Okay. So r of, excuse me, I'll write it out so we can see it. R p of x, which is r of p of x, which is r of, and then remember p of x is negative 2x, so negative 2x, okay? And so then what we're going to do is, okay, so I have negative 2x, and I'm going to put that in for this x right here, right? So it's going to be negative 2x plus 4, which is negative 2x plus 4, because there's no combining. So you'll notice that p of r of x is this, and r of p of x is this. So are they the same? They are not, okay? And that's important for something that we're going to talk about later on. Okay? So we can also have, sometimes what we're going to do is we're going to actually use composites of themselves, and then we can also evaluate it, right? So we said p of x is negative 2x. So what if I did this? Pop p of x, right? What would that look like? Well, that would be p of x, right? And so that would be p of negative 2, right? Because p of x is negative 2. And then I do it again, right? So it's going to be negative 2 times negative 2x. And so that ends up being 4x. So it's interesting that this gives us this in the end, right? But what if we were actually going to be asked to evaluate? Okay, so what if I was asked you to do the pop of 4? Well, that means that I'm actually just finding out, instead of using x, I'm going to put a 4 in. So I get 4 times 4, which is 16. Or maybe a better example would be the pop of negative 1. So that would be 4 times negative 1, which would be negative 4. Okay, so there's lots of ways that we can evaluate these. We can make these do different things, all kinds of good stuff. All right, well, what if we were actually going to look at a problem where we were given a function, right? Let's say we're given a function p of x, right? And let's say we're given a function p of x, and it's actually equal to g of f of x, okay? So p of x is really a composition of g of f of x, right? And our job is to find out what g and f of x are, okay? Now, let's say, so this is what we're going to do. Find f of x given g of x equals x squared. So let's say that they give us p of x equals negative 3x minus 10 quantity squared, okay? So we said p of x is really g of f of x. So I'm going to rewrite it this way. G of f, actually, in fact, I'm going to write it the other way. G of f of x equals negative 3x minus 10 quantity squared. Okay, so we already know that this g right here, okay, this g is x squared. So that's kind of good. So we're saying that this f of x is everything within our squared, right? So that means that f of x is going to be what we're squaring, and so that's going to be negative 3x minus 10, right? So we found f of x given that g of x is x squared, and we could check our answer by saying, okay, so g of f of x, if I was going to put this function into x squared, I'd take this and square it, and notice that's what I get for p of x. All right, so we can compose these or decompose these by looking at what they can be. And intuitively, it might not be as easy to begin, but the more problems you do with this, the more it will make sense. And if you have more questions, please don't hesitate to ask. Okay. Last thing we'll do is do sort of a modeling problem. Okay, and we do this all the time. Especially when we're looking at like coupons and discounts and stuff like that. So let's say that I'm going to go buy a new bike, okay? And my new bike costs $109.99, okay? Now, I look in the flyer and I see that I can have a 15% discount. And I also have a coupon for $10 off. Okay, so if you think about it, there's two different functions going on, right? There's the function of the discount, or there's the function of the $10 off. Now, let's say I go to the store and they actually said, yeah, you can use both of them, okay? And it doesn't matter to us which one's a better, or which one you do first, right? Do you want the $10 off coupon first and then the 15% discount? Or do you want the 15% discount and then the $10 off, okay? So this is a composition of functions. So let's say that this is our discount. So d of x is this. It's 15% off, which if it would be, and we'll just say coupon c of x is $10 off. Okay, so if we're going to write this a little bit more mathy, okay, we'd say d of x is really going to be, okay, well, x is the cost of our bike. And so a 15% discount, you're taking away 15%, which means that you're going to be paying 85% of x, right? And then the coupon of x would just be x minus $10, right? So you'd be taking away $10, okay? So we're going to look at this both ways, right? Let's say we do the coupon first and then the discount. So we would call this d of c of x, and x being the price of our bike, right? So we're doing the discount of our bike, which would be at, $109.99 minus $10, right? And so that would be 0.85 times 99.99. Okay, go to our calculator and we find that that's going to be $84.92. $84.92. Okay, so you go up and you say, all right, I want to take my coupon off first. And then after I'm not done with my coupon, then I'm going to take the 15% discount. I end up paying $84.92. Okay, good. That's a good price, considering it's normally like $110. That's a pretty good price. But now let's say instead you want to think about it and say, is it better to get my discount first and then take $10 off? Okay, so we're doing C of 0.85 times 109.99. Okay, and so what that means is, okay, we'll go to our calculator and we do 85% or 0.85 times 109.99. I get 93.49. So the coupon price of 93.49. And so that's really 93.49 minus 10. And so that ends up being 83.49. Okay, so if you look at it, the price difference between the two ends up being almost $1.50 in difference, right? It's almost, you save $1.50 by doing the discount and then the coupon. Okay, so super interesting. So this is actually a pretty good application that we could use, and we do this all the time when we're making decisions based upon all that kinds of stuff. Okay, so if you have any more questions, or if you have want to do another problem or anything like that, please feel free to email me and let me know. Good luck, and we'll see you soon.